If you need to solve a system of 3 linear equations, direct methods like Gaussian elimination work perfectly. But when you apply those same direct methods to the massive 10,000 by 10,000 sparse matrices generated by modern networks and physics simulations, the calculations hit a wall. That processing failure happens because direct calculation requires roughly n cubed over 3 operations. For a 10,000 variable system, that means executing trillions of arithmetic steps. At that scale, tiny rounding errors in the computer's memory compound with every single calculation until the final answer is completely destroyed. To bypass this computational bottleneck, we can use iterative methods. Instead of trying to calculate the exact answer in one massive sweep, we guess an initial solution and run it through a loop, refining the answer step by step. But to do that safely, we need a rigorous mathematical guarantee that our loop is actually moving toward the true solution, rather than wandering off into infinity. This flowchart lays out the 2 strict prerequisites needed to secure that guarantee, using the Banach Fixed Point Theorem. First, our data must live in a complete metric space, meaning there are no gaps for our sequence to fall through. Second, our iterative loop must be a contraction mapping, which means every step is mathematically forced to squeeze points closer together. By translating our massive matrix problem to fit inside this Banach framework, we swap computational brute force for a process that naturally gravitates toward the correct answer. To make that translation, we have to reframe the standard linear algebra format. We need to convert the familiar ax equals y structure into a fixed point format, which looks like x equals t of x. Looking at this expansion, we start with ax equals y. We can add x to both sides and rearrange the terms to get x equals I minus a times x plus y. Let's rename the I minus a matrix to C and the y vector to b. We now have our target form, x equals cx plus b, with the x variable isolated on the left and acting as the input on the right. If we define our mapping operator t as that entire right side of the equation, the logic aligns perfectly. Solving our original system of linear equations is now identical to finding a fixed point of t. This matrix C gives us the strict rule for making the theorem work, defined in Theorem 5.2-1. For this mapping to be a valid contraction, the sum of the absolute values of the coefficients in every single row of C must be strictly less than 1. That row sum limit acts on our contraction factor, alpha. If that condition holds, the geometry of the system guarantees that a single, unique solution exists. To prove this contraction works, we measure our vectors using the max metric. As shown in this diagram, the distance between 2 vectors, x and z, is simply the largest single difference between any pair of their corresponding components. When we calculate the distance between our mapping outputs, the constant b terms cancel out. By factoring out that maximum vector difference we just defined, we're left with the summation of the matrix coefficients. And since we already confirmed that row sum is strictly less than 1, the outputs are mathematically forced to be closer together than the inputs were. We can see this in practice by applying the Jacobi iteration. To generate the x equals cx plus b structure, we isolate a single variable xj in each equation, and then divide the entire row by its diagonal coefficient, ajj. Take a moment to test this out yourself. Pause the video, look at this 3x3 system, and try isolating x1, x2, and x3 by dividing each equation by its diagonal value. Calculate those resulting row sums to see if they trigger a contraction. Since every coefficient in that row was divided by the diagonal element, the sum only stays below 1 if that diagonal value was significantly larger than the others combined. This is why the Jacobi iteration requires the matrix to be strictly diagonally dominant. The algebra itself shrinks the coefficients until they satisfy the contraction condition. This inward spiral makes the method self-correcting. A rounding error simply becomes a new starting point, naturally about to center. And using this error-bound formula, we predict the maximum future error using just the very first iteration step. This comparison table shows why the method is so powerful. Direct methods offer theoretical exactness, but are fragile and slow down exponentially. The Banach iterative method provides an approximation, but it is fast for sparse matrices and inherently recovers from numerical errors as it iterates. The workflow is a precise 4-step process. Convert the system, verify row sums, iterate the formula, and trust the contraction. Banach's theorem provides the practical mathematical engine that allows computers to solve massive, complex systems of equations underlying modern physics and digital networks, utilizing self-correcting iteration to ensure accuracy at the largest scales.